ladies and gentlemen, without further ado, Craig.
Hey everyone. Just give me a little bit more back. Give me some confidence. Hey everyone. Hey, that's better. Thank you. I was just thinking about my colleagues when I was walking down here, and I was thinking about who I am a little bit, and I was like, oh, do you know what? I'm a little bit dramatic at times. They might laugh at that a little bit more. So I want to start with a little bit of drama. I want to tell you a true story about the greatest heartbreak of my life. It's 10:59 a.m., Friday the 13th of March 2026, 1 minute before general sale, for tickets to see Leslie Odom Jr. reprise his legendary role as Aaron Burr in the greatest show of our generation, Hamilton. Yes, there's some fans in the room. Those of you who know will understand how high the stakes are right now. So back to the story. I'm set up with my 2 laptops, my phone, my iPad, with my target in sight, and the clock ticks over to 11 a.m. Attempt 1 crashes. Attempt 2, the website crashes again. I try again on the laptop, and I see this. You are 132,442nd in line. This is an outrage. But I'm a developer. I know this isn't Ticketmaster, this is a theatre's own website, and I've already seen a number of bugs. Maybe there's a way around the queue. I try my phone, and bingo, I'm in. No queue, but I do see a timer. The session's 10 minutes, and if I don't complete the booking in time, I have to start again, and the timer is already counting down. I lock in. By minute 7, dates are found. By minute 5, I've got the perfect seats. By minute 3, my payment details are entered, but there's no Apple Pay. So the next thing I see is this: confirm in your banking app. Sweet, we're really there. We're nearly there. Nothing can go wrong, right? So I head over to my banking app. I don't see anything. I refresh, I close the app, I open the app again, refresh, nothing. Eventually it shows up, I press it as fast as I can, I head back to the ticketing site, and I see this. My heart was broken. After this, I went back on and spent the next session looking for affordable tickets, but I couldn't find any on the dates that I wanted. My dreams were crushed. It had taken 4.5 minutes for those confirmations to show in the banking app. This is what happens when traffic strikes beyond expectations. I don't know what the infrastructure is that handles payment confirmation requests, but I imagine somewhere it was sat at the end of a really long queue. And at the end of these technical issues are normal people like you and me going through real heartbreak. Hi, I'm Craig, and I'm a DevOps engineer at PassEntry. Standing up in front of a room full of Ruby engineers at a Ruby conference as someone who's not a Ruby engineer is a little intimidating, I must say. So let me tell you a little bit about myself before I introduce the topic of this talk. I got into tech the same way at least a few of the people in the room did, by doing the Wagon bootcamp, which allowed me to dip my toe into the Ruby ecosystem. I then went on to work as a software engineer for a few years, but not working with Ruby. And joining PassEntry as a DevOps engineer, I was able to bring myself back into the Ruby world. Running background jobs at large scale for multiple clients is a core part of many businesses. And today we're going to go through a few strategies to isolate workloads at scale and minimize contention with your background jobs so you can help your end users avoid heartbreak. Okay, so we're going to look at 3 different workload isolation strategies today. Firstly, per client. Secondly, shortest queue. And finally, shuffle sharding. As we explore solutions ahead of us, I want to look at them through the lens of affordability, scalability, and acceptable risk. No solution is perfect, so assessing and documenting these factors can help you understand if any solution is right for your business. Let's take a brief moment to talk about stages of a business growing. Early, we ship fast. We have small infra, We move quickly, we're breaking things on Monday and fixing them by Wednesday. Then we start to grow. Real traffic shows up. We're having our first outages, capacity conversations. We need to be responsive to the needs of clients that we may not even know yet. And once we hit scale, there's much higher pressure to mitigate risk, protect and maintain the service for our customers, even as we build and deliver new features and business value. There are two key shapes of traffic that we need to consider. Firstly, constant traffic. We know how and why and when we get this traffic. We can assign the appropriate resources and even predict growth. Then we have spiky traffic. This is unpredictable. It's inconsistent, and we may not even know why. We have to look back at what happened in the past and always provision for the worst-case scenario. Looking at this graph, you can see all of the gaps below that red line. That's unused compute and potentially wasted money. So what does this look like at PassEntry? PassEntry is a digital wallet provider. I'm sure you all have passes in your Apple and Google wallets, train tickets, gig tickets, or even shopping club cards. In a nutshell, that's what we do. A large part of our offering is messaging. So let's look at one use case that brought this issue to life for us. Fan passes. Many artists have fan passes to give exclusive offers, early access, and event information. All of these actions boil down to one key function: bulk messaging. Many of you may already be aware of the challenges involved in bulk operations and loading hundreds of thousands of background jobs and processing them as fast as you possibly can. We're going to have a look at what our infrastructure looked like way back then. Originally, we had one shared worker pool listening to low, medium, and high queues. There's a little bit more than that, so I'm sure my colleagues are kicking me right now for oversimplifying. Messaging is a top priority for us. So all messages go into our high queue and are prioritized over everything else. We regularly get batches of a few thousand, scale our worker pool based on job queue time. We had a lot less clients at the time, and message batches would process quickly, never causing significant wait times for other background jobs. The solution was an acceptable risk for where we were at. Then we onboarded these handsome chaps. With 2 Grammys and a Brit Award, it's safe to say they have a bigger fan base than the other artists that use our platform. So on a peaceful Friday evening, because of course it's always a Friday evening, they sent a bulk message to all of their fan pass holders. How many, you ask? 400,000. At this point, there's nothing we could do but watch it burn and wait for it. Yes, Hamilton fans. And wait for it to die down. And of course, start writing our apology emails. At this, we were outgunned and outmanned. Even though messaging is the most important thing for us, this was like trying to swallow a cow. So what happened? Once Mumford & Sons sent those 400,000 messages, it hit our high queue, and even scaled to the maximum, it would take an hour to process. The real issue is all other jobs had to wait, causing many of our services to grind to a halt. So what can we do about it? The first thing to consider is weighting your queues. This will ensure low-priority jobs will still be processed, even if the high queue is busy. However, one client can still monopolize the high queue with large batch messages. It's helpful, but it's not enough. We could also consider setting a queue per client equally weighted with the high queue. This helps, but it doesn't scale well. Each new client requires an update to your Sidekiq config and the operational overhead, and also adds time to the contention. All clients are processed slower, and as the number of dedicated queues you add, you share that probability with all of those clients. Both of these ideas ease the symptom, but neither cures the underlying contention. So let's talk about sharding. In this context, we mean dedicated compute and queues for different use cases. The first thing to consider is decoupling operations. In our case, we decided to split the time-bound background jobs from the bulk background jobs. Bulk background jobs can now only impact other bulk background jobs. Excuse me. This added the bonus of allowing us to use different strategies for scaling. Time-bound jobs use queue time, and bulk jobs use queue depth. Now let's go back to our per client model and see how this works with shards. If we set up a queue and worker pool for each client, we guarantee workload isolation. That sounds great. This seems fine as a good tactical solution in a pinch, but it's not great as a long-term strategy. Let's see what happens when you onboard new clients. Our bulk infrastructure has doubled in size as our business keeps growing. Our client base has now tripled, but so has our infrastructure. Is this affordable, scalable, and with an acceptable risk? You could argue no to all of these. Our costs are now scaling based on users, not on usage. It's not easily extensible. Sidekiq config needs to be updated and compute deployed for each new client. It's likely the majority of this compute is going unused for the majority of the time, and it becomes difficult to predict resource usage like database and Redis. As the number of clients grows, our database connections and Redis connections can get out of control. So I wanted to share with you a little snapshot of what our traffic looks like to our bulk queues. As you can see, there's huge periods of time where absolutely nothing is happening. Then all of a sudden, we're slammed with a lot of jobs at once. And I don't know if you can see from where you are, but there's multiple colors on there. And this is multiple clients. So there is some crossover, but the main point is there's a lot of time where clients aren't doing anything. They want to send a messaging campaign 2 or 3 times a week. And when you're in that growth stage, this is really what it looks like. So the perfect solution is a potentially limitless expense. So let's reframe the question. What probability of this event happening are we willing to accept? Consider this model. 2 bulk worker queues that only process one, two bulk worker pools that only process one bulk worker queue each. Each worker pool can scale when traffic hits, but at rest, it's as small as possible. Each time a batch message is sent, we route it to the shortest queue. Mumford & Sons send 400,000 messages. Both queues are empty, and bulk 0 is selected to process the batch. Whilst they're processing, Kendrick Lamar also sends 10,000 messages. Now both queues are in use, and Lauryn Hill wants to send 20,000 messages. Those messages are queued behind Kendrick Lamar's. We know that we can process 30,000 messages within our SLA. We reviewed our previous traffic and decided this was an acceptable risk. But what do we do when that's not enough? It's simple. We add another bulk queue. Let's look at the rationale behind this. Each shard you add reduces the chance of a collision. When 2 clients want to send messages at the same time, and you only have 1 queue, 1 worker pool, there's a 100% chance of a collision. By adding the second, we reduce that to 50%, and the third brings it down to 33%, and so on. It's always 1 over the number of shards to find your collision risk. You're now scaling the infrastructure based on the agreed acceptable risk. Even operationally, this can be managed. At PassEntry, all I need to do is deploy another worker pool, and it is automatically picked up as an option to process messages with no config or code changes. Is this affordable? Yes. Is this scalable? Yes. So my advice with bulk queues is to run them small instances, keep costs low at rest, scale up aggressively when demand spikes. Just a caveat, this is also how you DOS your own database, but this is a topic for another talk. Scale down in lockstep. There's no point holding capacity you don't need. Just keep enough to maintain your desired throughput. The final solution we're going to look at today is shuffle sharding. Quick context before we get into the mechanics. Shuffle sharding wasn't invented for background jobs. It came out of AWS's Route 53 for DNS team. The problem they faced was DDoS. If you put all your customers on one big fleet, one customer getting attacked takes down everyone with them. But giving every customer their own dedicated infrastructure doesn't work at DNS scale. You can't buy enough hardware to isolate millions of customers. It's not scalable or affordable. So shuffle sharding was a clever software answer. Assign each customer a random combination of nodes from a shared pool so that only 2 customers at most ever share the same exact set. So that no 2 customers ever share the same exact set. An attack on one customer only degrades a handful of nodes in their shuffle. Everyone else's combination stays mostly intact. You get the isolation benefits of dedicated infrastructure and the cost of shared infrastructure. Mike Perham, the creator of Sidekiq, translated this idea into queue sharding with Sidekiq in a 2019 blog post. This implementation is similar to shortest queue. However, you would always randomly select the queue, so there truly would be a chance of messages waiting behind Mumford & Sons' 400,000 jobs. So, we're going to jump into a little example of the last solution. If your business has reached a really large scale, and you want to do something similar to focusing on redundancy, but you're really focusing on redundancy and isolation, you can assign your clients a subset of shards with other clients. If client A sends a batch of messages and is picked up by bulk queue 7, it won't block client G as they have other shared resources available to use. With this model, you can assign more clients to more queues and reduce possible contention. So you could assign 3 queues to each client or 4 queues to each client. Doing this reduces contention but maintains isolation. So each of these strategies has the same building blocks with different pros and cons. Per client is predictable but wasteful. Shortest queue balances the load well but can still be blocked. Shuffle sharding has a tiny blast radius but has a lot of moving parts. We've explored a specific technical implementation of queues and sharding. However, discussing these issues through the broader context of your problem solving is really helpful. No solution is perfect. If we treat acceptable risk as a feature, hopefully there'll be fewer hearts broken like mine. So if you want to know more about shuffle sharding, check out these 2 articles, one by AWS and one by Mike Perham. Or you can just come and chat to me later, or if you want to chat to me about anything else. Thank you for listening.